Hi everybody, it's the 25th of March in 2020 today. I hope and pray that you're all staying safe and healthy from the coronavirus. You can see I'm at home trying to finish off my semester with my students at Bethel University in St. Paul, Minnesota. And I'm going to be recording lectures for a class called Applied Statistics. I'm also going to be recording some lectures for a class called Numerical Methods, and possibly doing some other things as well to finish off the semester. Applied Statistics, what kind of class is that at Bethel? You could more descriptively call it Advanced Undergraduate Statistics. It is calculus-based, and we're going to be doing some pretty advanced things. You can see that Lecture 17 here in the middle of the semester is going to be a review of what we've done about simple linear regression, plus some new material that I haven't talked with my students about yet. I'm going to try to make the content for this lecture and lectures to come available on a Google Drive for people around the world. And also for my students at Bethel on Moodle. I haven't tried that before, so I hope it works. And we'll see, I guess, if it works or not. Bethel University is a Christian university, and I want to start actually by reading from the Bible. Now, if you're not interested in that, if you want to just go ahead and jump to the statistics lecture, I will put a timestamp in the description below, and you can just go ahead and jump to that. But I'm going to toggle through things. I'm going to toggle through PowerPoint, Mathematica, a spreadsheet, and also some writing that I do. And here you can see on a dot cam I've got Psalm 23. I think would be an appropriate chapter from the Bible to read to give you some encouragement, to help you trust in God for both your salvation and to see you through this crisis. So I'm going to start by reading that, and you can listen and maybe pray along with me. The Lord is my shepherd. I shall not want, meaning I have everything I need. He makes me lie down in green pastures. He leads me beside still waters. He restores my soul. He leads me in the paths of righteousness for his name's sake. Even though I walk through the valley of the shadow of death, I will fear no evil, for you, God, are with me. Your rod and your staff, they comfort me. You prepare a table before me in the presence of my enemies. You anoint my head with oil. My cup overflows. Surely goodness and mercy shall follow me all the days of my life, and I shall dwell in the house of the Lord forever. So, if you're a Christian, take comfort in that, believe in God, trust in God to see you through, and also trust in God to help you work hard. You still need to have things to learn, to finish the semester, to do well, to be the kind of person that God wants you to be. So please take that as encouragement here in the weeks and months ahead. Alright, so now I'm going to start the lecture. So we'll start in a PowerPoint here that I showed you at the beginning. Sorry, I'm on kind of a wobbly table here, so if it shakes a little bit, that's the reason. I'll do my best not to shake it as much as possible. I do have some extra things here that will help me. I've got some coffee right here that I might take a drink from once in a while. I have some water in case my throat gets kind of dry, which it tends to do sometimes. So this is going to take a while to go through. It's pretty detailed content. I want to focus both on big ideas and detailed content like formulas and things like that. And with my students at Bethel, you're going to get an added benefit out of this in that the next homework assignment, this first homework assignment after spring break here, is going to be directly related to this lecture and the formulas that I show you and the example that I show you. And you essentially just need to confirm the calculations for your first homework assignment here after spring break. So what is the lecture plan here? It's partially about the purpose of simple linear regression in the context of an example, and the example is tuition data at Big Ten schools in 2013 and 2019. We're going to look at what are called the normal equations excuse me, for simple linear regression. We've seen these equations before spring break. And you need to solve those normal equations to find the line of best fit, the linear regression line. And these normal equations have have an extra benefit. They allow you to generalize to higher dimensions, to the matrix vector form for multiple regression. That's going to be very handy for us. 3, the most important formulas and calculations you should check. In other words, like I said before, my students at Bethel University will be checking these as their homework, but if you are not at Bethel, you can still check them. You can try to download those files off my Google Drive and check them on your own. While I show you these formulas, which are very detailed, and there's a lot of them, And I'm going to try to emphasize the most important ones. I will be also reminding you the meaning of and the interpretations of the symbols and the equations. So it's not just a bunch of formulas. There's a geometric meaning, there's an interpretation, a real-life interpretation for these things. I'm also going to emphasize that to some degree, it is important to be able to think intuitively about the formulas. They should make a certain amount of sense, okay? Even if you can't prove them mathematically. Finally, again, like I mentioned, we're going to look at spreadsheet and Mathematica output and try to interpret that in the context of what we're talking about here. So here's the example, tuition at Big Ten schools. You can see this is the Big Ten. The Big Ten used to actually be 10 schools, but now it's 14 schools. And I never realized this before I made this PowerPoint here, that no schools start with the letter before I in the alphabet. That's kind of interesting. So we start with Illinois, then Indiana, Iowa, etc., on down through Wisconsin. And this is the in-state tuition yearly for 2013 to 2014, first of all, and 2019 to 2020. And you can see, as you would expect, the 2019 numbers are all bigger than the corresponding 2013 numbers. How do you deal with data like these? We're looking for a relationship between two variables, x and y. X is called the explanatory or predictor variable, and y is often called the response variable. We are going to typically think of x as being known, and y sometimes, at least, as being unknown. Now, of course, with these data, we can see what the values of y are, but we want to imagine this as really being, in a sense, a sample, a random sample from a larger population. Now, it's not truly random because it is truly Big Ten schools, and that's very specific. So it's not truly random, but it doesn't hurt in some ways to pretend it is, at least for some applications. And we would want to look at how the model that we construct predicts things about perhaps other schools. And we will, in fact, do that. And you'd want to make a graph of this with what's called a scatter plot. You can see the year 2013 tuition along the horizontal axis and the year 2019 tuition along the vertical axis. And we see that it follows a fairly strong linear trend. And there is an extreme outlier. What is the extreme outlier? Well, it's Northwestern University in Chicago. That is extra expensive compared to the rest of the Big Ten schools. It's kind of a wonder that it's actually in the Big Ten, I think, actually. But even though it's an outlier, it does still follow the trend pretty well. So that's pretty interesting, something that stands out right away. You see the trend line, that's the linear regression line. Also notice that some points are above the line and some points below the line. That's a natural thing to happen. In fact, it's a pretty rare thing that the regression line would go through any of the points exactly. That would be pretty rare. Okay? What about the equation of the regression line? You can see it at the top here, 1.2x minus 0.185. Ignore that r squared there for the moment. If you want more digits of accuracy, it would be this 1.2011592 times x minus 0.1852275. That's more significant figures than is warranted. However, I always try to emphasize this to my students, that it never hurts to use more significant figures than you need at first, and only round at the end, because if you round too soon, then the rounding errors build up. It's a regression equation. Sometimes the predictor variable is called y hat. By the way, the hat that you put above the variable just emphasizes that you're trying to make a prediction. In our book, which looks like this here, it's an advanced undergrad book on probability and statistics by Milton and Arnold. They typically write this as capital Y hat conditioned x, meaning given that the x value is a certain value. Kind of weird notation. If this is something new to you, don't worry too much about it. We're trying to predict y when we are given x. That's the upshot of this notation. This mu that you see here, where'd my cursor go? Oops. There it is. This mu that you see here emphasizes that we can also use the regression line to predict the mean. Mu represents the mean. The subscript here is the y hat conditioned on x, given that x is known. That's just emphasizing that is the mean of all those y values when you know x. You can use the regression line equation either way to predict the mean or predict an individual y value. Okay? it does a better job in some ways of predicting the mean because there's less variability in the mean. Less good of a job in predicting individual responses. All right, what are the normal equations? Well, first of all, you should know that the normal equations are obtained by minimizing something called SSyy, which is shorthand for sum of squares error. And you should also know that the word error doesn't mean mistake. It's synonymous with residual. I will be using those words, error and residual, interchangeably. We'll talk about what those mean here very soon. So we are trying to minimize something. That's why it's often called least squares linear regression. The least squares emphasizes that you're minimizing something. Given a data set, x1, y1, x2, y2, etc., through xn, yn, so n is the number of data points. And with the Big Ten data, we have 14 data points, so n is 14. Keep that in mind in all this. For our example, n is 14. The normal equations to solve for the intercept b0 and the slope b1 of the regression line are these equations in general. Okay, so again, for our example, n would be 14, so we could plug in n equals 14 right here if we wanted to. N, 14, times b0, which is unknown, the unknown intercept of the regression line, plus the sum of the x values, x1 plus x2 through xn, times b1. This is going to be some number, some fixed number when you got the data, when you got your observations, equals the sum of the y's. That's going to be a fixed number as well. So this is going to be a linear equation in the unknowns b0 and b1. Same kind of thing down here, except it's a different linear equation in the unknowns b0 and b1. The coefficient of b0 is the sum of the x's. The coefficient of b1 is the sum of the x squareds, meaning x1 squared plus x2 squared plus x3 squared, etc., up through xn squared. Equals, on the right side, you can see it's the sum of the products of the xi's and yi's. So that would be x1 times y1 plus x2 times y2 plus x3 times y3, etc., up through xn times yn. This is going to again be a system of linear equations in the unknowns b0 and b1 that you can solve to find, again, b0 the intercept of the regression line and b1 the slope of the regression line. How do you derive these equations? You can use either calculus or linear algebra techniques. In my applied stats course before spring break, we used calculus techniques. We took the derivatives of these equations, the partial derivatives, well, not of these equations themselves, but a different function. With respect to b0, b1, we set them equal to 0 and we solve for b0 and b1. Actually, we didn't literally solve for them. We set up the system of equations that they had to solve to be critical points of the SSyy function, which I'm going to show you in a minute here. We also will talk about very soon how to derive these with linear algebra techniques. We won't usually bother putting the I equals 1 and the n below and above the summation symbols. Okay, they will typically be understood that I goes from 1 to n. That'll save some writing, especially for you when you're trying to write things out. Okay, so that's the big idea of what's going on here. Now we're going to get into calculations to check. For this example, we're still talking about the Big Ten schools example, and this, again, for my Bethel University students, this is homework for you. I should warn you that the numbers are kind of gigantic. You're going to get numbers in the millions and even above a billion when you do these calculations. You could convert the numbers to, say, thousands or something to make them smaller and have decimals involved if you want. That's okay as well. But these are going to be some calculations to check, emphasizing the formulas that we did learn before spring break. And if this is new to you, this would be formulas that will be new, and you can work on trying to learn. The formulas are not the most important thing, I should say, at the outset, especially for users of statistics. But if you're going to be a math major or a stats major, you should know the formulas. And they do have the benefit of giving you some insight about some things, if you think about them in the right way, and I'll try to emphasize those things as we go here. I need to wipe my nose here a little bit. By the way, I'm perfectly healthy. I do have allergies, though, pretty badly. All right, so what's the equation for the slope, b1? When you solve the system of normal equations, b1 turns out to be this crazy-looking thing. b1 is SSxy divided by SSxx, which can be simplified as you see there. And finally, when you finally plug in the numbers and completely simplify, what you should get, and this is what my students should check for their homework, you should get 1.2011592. Okay, what is this SS? What are these SS symbols? I haven't talked about what those are. I can say partially what they are here in a minute. And the formula for the intercept is much simpler looking. It's y bar, the mean of the y's, minus b1, the slope you just found, times x bar, the mean of the x's. And you should check that that turns out to be approximately negative 0.1852275. Where we got some other quantities here. We should maybe look at these right away. Okay, I guess I haven't said what the SS's are. SS does stand for sum of squares. And I don't want to get into the details of what SSxy and SSxx are from their definitions, but just take it to the bank that SSxy does equal this thing in the numerator of this fraction, and SSxx does equal the denominator of this fraction. And then this fraction can be written this way if you multiply the top and the bottom of this fraction both by n, meaning you'd be multiplying the whole fraction by n over n1, which does not change it. What are some other things you should know? The sum of the squares of the errors, SSyy, we talked about this on the previous slide, is defined to be the sum of the EI squareds, where the EIs represent the residuals. Those are the errors. I'm going to show you a picture here in a minute to illustrate these errors. The vertical distances between the points, the data points, and the regression line. So the yi represents the second coordinates of the data points. Yi hat represents the predicted second coordinates that come from the regression line. Assuming we know what b0 and b1 are, you can plug xi into the regression line equation, b0 plus b1 xi, to find yi hat. And when you do these differences and square them, I forgot to put a square here, you're gonna get 9. What would this be here? This is going to be 9,967,000.414. There is a typo here. There should be a square here. I should probably fix that typo right away so I don't forget. So you're watching me fix a typo here as we go. There should be a square in there. Come on, my computer's running a little slow here. Here we go. This should be squared right there. Sum of the squares of the errors. This is the thing that we minimize with calculus techniques as a function of b0 and b1. That's the thing that we minimize when b0 and b1 are unknown. But here, when you use this equation to confirm that it equals this number, b0 and b1 are known. They are what the numbers that you see right there. You can also calculate SSyy in another way, and my students should check this too for their homework. You can calculate it as SSyy minus b1 times SSxx. SSyy turns out to be this thing, SSxy turns out to be this thing, and b1 we found to be this. That confirms to be the same thing. If you look in this book, I'm not going to try to find the page, it's later in chapter 11, you will find that formula here, SSyy minus b1 times SSxy. The book, though, doesn't use the double S's, they use just a single S. I like using SS for sum of squares. Then we have the regression standard error. It's the square root of SSyy divided by n minus 2, and it's about 866.071947. But wait a minute, what does all this mean? I mean, if this is new to you, you're like, what in the world is all this? I mean, I kind of get the idea of the slope and the intercept, but what is all this other stuff? Well, that's where I want to now go and look at Mathematica. If you don't know or have Mathematica, it's okay. You can still get some big picture ideas out of what I'm going to show you here. So here I have the tuition data, year 2013, year 2019, and Mathematica needs to go into Mathematica's memory as what are called lists. That's why the curvy braces are there with the numbers separated by commas. And if I do this kind of function, use transpose in this way, it's going to create a list of data points. And I'm storing these points, you can think of them as points, in this variable that I'm calling data points by entering that. Once it's entered, I can recall it by typing data points and seeing there's the numbers that I just entered, the points. There's some built-in Mathematica functions, fit and linear model fit, that are going to allow us to, well, find the regression line and do some other things. Fit just finds the regression line. Here it is. Okay, so there you see the intercept, negative 0.185228, plus the slope times x, 1.20116 times x. That's what fit can do for you. Very quickly give you the equation. We can also use something called linear model fit. Now, linear model fit is more advanced. It does more than just find the equation, the regression line. It does pretty much anything you would want to do in statistical inference with regard to the regression line. It can do other things, as we will see below. When I enter this code, it's not going to do anything seemingly, but it is going to store some things in a variable I'm calling LM for linear model. And then I can access that information by doing various other commands, using various other functions. Normal will allow me to see the equation in its normal form, you might say. And I can now plot that equation along with the data points with this code here. So this is the picture that it was on the PowerPoint. We see the data points in black, we see the regression line in red. I do want to remark before I go on that because you've got this extreme outlier here, that regression line can be very sensitive to changes in that outlier. It's sometimes called an influential observation. Especially, well, you know, it does sort of closely follow the overall trend here. But especially if it doesn't follow the trend, it can greatly affect the regression line. Like if I put it way down here, it can even make the slope of the regression line negative, even though the main trend here for the main bulk of the data points is a positive trend. If it's closer to those points, then the regression line is going to go back to having a positive slope. But if it's really far away, it's very influential. It can, just at one point, make the regression line have a negative slope. So you want to be aware of those kinds of things that can happen with outliers in regression sometimes. All right, there's other things linear model fit can do, but I think for the moment we'll leave it at that. Oh, I should emphasize, though, that the residuals, again, these errors, are vertical distances between these points and the regression line. So you've got this point here, that might be 2 points. That's got a vertical distance to the regression line. That would be positive because it's above the regression line. Yi would be bigger than yi hat. With a point that's below, like this point here, that's going to actually have a negative residual. The residuals are not truly distances, they're sign distances. When the points are above the regression line, they're positive. When they're below the regression line, they're negative. Yi is going to be below yi hat for this point, and so the residual will be negative. Again, sorry about the shaking of the table. There's nothing that really can be done about this, I think, other than me just being as careful as I can be. What is this last thing, this regression standard error? Well, in a nutshell, sigma, forget about the hat for the moment, but sigma is the standard deviation of the y values for any given x value. That's the assumption of the model, is that sigma is the standard deviation in the y values, the response variable, when you know x for any given x in the model. We'd want to estimate what that standard deviation is, and you do it by calculating this thing called the regression standard error, labeled either S in our book, or many people label it SE to emphasize it is a standard error. It is the square root of SSE divided by n-2, and there are n-2 degrees of freedom with simple linear regression. I'm not going to get into reasons why there are n-2 degrees of freedom. There's a real technical kind of thing as far as proving it, why you would do that. It's related to something called unbiasedness of the sample variance for the regression. The derivation of that proof of that is very complicated. I did find some videos that give you some intuition about it, and for my students I'm going to send you links to those. In fact, I guess I could do that for everybody. In the description below I can send a link to some videos that give you some intuition behind why the degrees of freedom is n-2. More calculations to check. Okay, so there's lots of formulas here, okay? And again, the formulas are going to feel overwhelming, especially if it's new to you. For my students, this is stuff we have seen for the most part before spring break. So it's a review for you, and I want you to get back in the habit of practicing them. I need some water here. I am going to draw on some paper here to try to emphasize the meaning some more as we go, including that regression standard error. I'm going to re-emphasize that. In fact, right now I'm going to make some drawings. What is something called the standard error of B1? And notice this is a capital B1 instead of a lowercase b1. In advanced probability, like you find in this book, we typically reserve capital letters for random variables, okay, which are kind of an abstract idea. Random variables can be discrete or continuous or mixed random variables, and they have what are called distributions. They have probability density functions in the continuous case or probability mass functions in the discrete case, and cumulative distribution functions. And these are functions that describe probabilities related to these random variables. And it's all pretty abstract. Lowercase letters are reserved for observed values of the random variable when you perform a random experiment. So when I talk about a lowercase b1 here, I'm talking about an observed value of a slope of a regression line, a sample regression line we're trying to use to estimate a population regression line. Okay? Capital B1, though, is a statistic in the abstract. It's a random variable. It's got a distribution. It's got a probability density function, actually. And the standard deviation of that can be estimated by this equation that you see here, where S is that regression standard error, which I also labeled S sub E, divided by square root of SSxx, sum of squares of the x's twice, which was on the second or third slide. And my students should check that for this situation, this equals about 0.025004896. What does this mean? Let me go out of the PowerPoint and go to my .cam here and try to emphasize the meaning of this. B1 is a statistic. Capital B1 is a statistic. What kind of statistic? It's a random variable. RV stands for random variable. What kind of statistics? Well, it is, excuse me, continuous. It's the theoretical slope that we could calculate from a random sample. When we're sampling two variables, a predictor variable and a response variable, where really the predictor variable, the x's, are typically thought of as known, and we're really trying to observe the random possibilities in y. If I write down that formula for the slope, in fact, I'll show it to you again here. This thing right here, B1, and if I think of the y's that you see in that formula as capital Y's, meaning they're really random variables, random responses to given x's, then that thing is a random variable because the y's are random variables. And therefore, it's got a distribution. It's got a sometimes called a sampling distribution, which in the model we assume the y's are normal, so actually B1 has a normal distribution as well. Its distribution, its sampling distribution, looks like a normal curve. Turns out to be an unbiased estimator for the population slope, which is, well, here's a new letter called beta 1. That's a beta, a Greek letter beta. The expected value of B1 equals beta 1. B1 is an unbiased estimator for beta 1. What does that mean? Well, it means this distribution is centered on beta 1, so in random sampling from this wider population, about half the time the observed value of capital B1 would be higher than beta 1, and about half the time it would be lower than beta 1. Okay? This distribution also has a standard deviation, and since it's a normal distribution, the standard deviation is represented by this distance right there, where this is supposed to be the inflection point of this curve over here, where it changes from concave down to concave up. You could label that, say, sigma sub B1, the standard deviation of B1. And we have just said that it's approximately, based on what we've got with our sample data, this is approximately 0.025. Approximately 0.025. Pretty small. Okay? Beta 1 is unknown. We're trying to estimate beta 1 with B1. In fact, our point estimate for beta 1 would be this number, 1.201592. We hope it's close to beta 1, though it's not likely to be exactly beta 1. That would be where this distribution is centered and would have this kind of standard deviation. So, for example, in about 68% of all samples, you'd be within one standard deviation of the mean. You'd be between beta 1 minus approximately 0.025 and beta 1 plus 0.025 in about 68% of all samples. Very theoretical, okay? This is an advanced statistics course. My students should feel fairly comfortable with that, even though it's a pretty hard thing to get your mind around. Take a breath. We also want to know what's called the t-statistic to test for significant regression. I'm trying to emphasize the most important things here. We want to do this test that you see here. The null hypothesis is that beta 1 is 0, that the slope of the population regression line is 0. And the alternative hypothesis when you are testing for a significant regression is two-tailed. Beta 1 is not 0. Okay, that's the main test I want to emphasize when we do Chapter 11 for my students. How do you do this test? We need to calculate a t-statistic and then a p-value. Here's the t-statistic, and my students should double-check this. Lowercase t because it's an observed value. If it was a more abstract random variable, I'd call it capital T. And I'd use a capital B1 as well, but I'm using a lowercase b1 now because it's an observed value. When you use that b1 value from the other slide, S, the regression standard error from the other slide, and square root of SSxx from the other slide, it should simplify to about 48.03695.972. DF, keep in mind, is 12 here because n is 14. And we could use this to then calculate the p-value for this two-tailed test. It's a very small p-value. It, in scientific notation, is about 4.3 times 10 to the negative 15. If you're using a table from the book, it's sort of off the chart, and you'd say it's essentially 0. But you can use a calculator to double-check this as well. In fact, my students should take the time to do that. And it does give it to you in scientific notation to be about, again, 4.3 times 10 to the negative 15. Super duper small. Definitely reject the null. We definitely have a significant regression, okay? Meaning it's worth doing. If we could not reject the null, then we'd be like, well, should we really be doing the regression? Because we don't have significant evidence against the assumption that beta 1 is 0. We're trying to see how x affects y. If beta 1 is 0, then x is not affecting y. How about a 95% confidence interval to estimate beta 1? Here's the formula, and you should check that this is true based on the numbers that I've given you. We do need to use t sub 0.025 based on 12 degrees of freedom. That means the t value where with 12 degrees of freedom, the area to the right is 0.025. And I'm forgetting offhand what that is. Maybe I should look it up. I think it's about 2.1 something. Yeah, it's 2.179 is what that t value should be. I'm looking that up in a table. More calculations to check for homework for my students. Confidence intervals and prediction intervals to estimate means for confidence intervals and to estimate observed values for prediction intervals. I'm going to show you how this all turns out in Mathematica and a spreadsheet as well. So 95% confidence interval to estimate the mean response of y when x is known to be, I picked the number 7,681. Why did I pick that number? Well, I decided to look for the average tuition of Minnesota state schools. Now, University of Minnesota is the biggest university in Minnesota, and that is part of the Big Ten. Its tuition is higher than this. Minnesota state schools include things like Mankato State University, I think St. Cloud State University, Moorhead, maybe Minnesota Duluth. Their tuition on average is lower. They're smaller schools. And their average tuition in 2013 is what this is. It was 7,681, at least based on the source that I found. I'm not guaranteeing that that source was correct. Here's the formula to estimate the mean of the y values, meaning the 2019 tuitions. Now we're talking application here. The 2019 tuitions for Minnesota state schools when we know their 2013 tuitions. And we might be interested in knowing how it compares, well, when we use this predicted, how it compares with the actual data. And actually, I think I didn't look that up, so I don't know for sure. I might have put it in the spreadsheet. So to find mu hat, you need to use the regression line equation with the slope and the intercept that we found. You should get it to be about 9,226. So this is the point estimate your prediction for the tuition at Minnesota State schools on average in 2019, based on knowing in 2013 it was 7,681. Plus or minus a margin of error, and the margin of error is this t-value, which again was like 2.179-ish, I think, times s, which is SE, the regression standard error, times the square root of 1 over n, plus the x value you're interested in, this case 7,681, minus x bar, quantity squared, divided by SSxx. If I was interested in another x value other than 7,681, I'd plug in a different x value here, whatever x value you're interested in. And you get this interval of numbers. It's a 95% confidence interval. What does this mean? It means I'm 95% confident if the sample truly were representative of the population, if it were truly random, which again it's not, but if it really is representative of the wider population of all schools. So among all schools whose 2013 tuition was 7,681, I'm 95% confident that the mean tuition in 2019 for all schools is in this interval, okay? Which is a pretty wide interval here. So I got a fairly wide amount of leeway. Prediction intervals are even wider. We're trying to estimate individual responses. Individual schools' 2019 tuition when we know that their 2013 tuition was 7,681, or at least approximately that. Of course, it's probably going to be unlikely for any school to have exactly that tuition in 2013. So this is going to estimate, again, not the mean of all such schools, but an individual next observed value. And it's got to be wider because there's more variability in individual observations than there are in means. A little funny notation here, y hat, given that x is 7,681, is supposed to be the number you get from plugging into the regression equation. Same point estimate, 9226, as before. But you can see the margin of error does end up being a bit bigger because of the extra +1 in there. And you can see the margin of error is actually over 3 times bigger because of that, and you should double check that. You might wonder, how can adding just a +1 in there make the margin of error 3 times bigger? This is where some intuition, some logical thinking comes into play. Well, in general, the thing under the square root here is a pretty small number. This thing under the square root is probably a pretty small number, pretty close to 0. When you add 1 to it, we then get a number under the square root that's a little bit bigger than 1. The square root of a number a little bit bigger than 1 is also just a little bit bigger than 1, which could be orders of magnitude bigger than this number that's close to 0. In this case, it's over 3 times bigger. Okay? Think about that. Plug in some numbers to double check that. It does work. Just adding a +1 here can make this margin of error orders of magnitude 3, 4, 5, 10, even 100 times bigger than this margin of error. It's possible, especially if this quantity here is very close to 0. What's the correlation and coefficient of determination? This is not something that my students have had a ton of time to focus on with me yet. It was in their reading from the book. Here they are, and you can use these formulas to find these things. R is called the correlation. It equals, it turns out, the ratio of SSxy to the square root of SSxx times SSyy, and is about 0.9974099 in this example. Correlations can be positive or negative. They're always between -1 and 1. When they're close to 1, you've got a strong positive linear relationship with a positive slope. When they're close to -1, you've got a strong linear relationship with a negative slope. When they're close to 0, it's not much of a strong linear relationship at all. It's either a weak linear relationship, or it's maybe a nonlinear relationship. Maybe it's a parabola or something like that could give you a correlation close to 0. R squared is called the coefficient of determination. When you square a number close to 1, it's also close to 1, so R squared is not much different than R in this case. But in general, when R is positive, R squared is going to be smaller than R, and this is a little bit smaller than this number. R squared is actually a little bit better measure of the strength of the linear relationship. This has more significance when R is something like, say, 0.5 to 0.7 or so. For example, 0.7 squared is 0.49, close to 0.5. Approximately a 50% coefficient of determination, a moderately strong regression, even though R itself, 0.7, is closer to 1 than it is to 0. An R of, say, 0.3 would give you an R squared of 0.09. Not very strong, actually. 9%. Okay, and we'll talk more about what R squared means at the end of the lecture here. So again, I'm not getting into details of how this is derived. This does approximate a population correlation, which is typically called rho, the Greek version of R. And we can test rho, and I'll talk about that later as well. In fact, I can talk about it right now. The t-statistic to test the correlation, whether the population correlation rho is 0 or not, has this formula, which my students, again, can find in this book, but I'm not taking the time to derive it. My students should confirm that it does equal 48.037. Kind of a strange formula. We still have 12 degrees of freedom just like before. One thing I do want you to note, however, is this number, 48.037, is the same as the t-statistic that we got back here, 48.037. I got more decimal places of accuracy there, but it is the same. Interesting. Is that a coincidence? No, it's not a coincidence. This t-statistic, when you know B1, SN, SSXX, is the same as this t-statistic down at the bottom of this slide when you know the correlation R and you know N, the sample size. They give the same answer. They give the same p-value for this test as the other test. We're thinking of the test differently. The other test, we were thinking of the null hypothesis as being beta 1 is 0, and the alternative is beta 1 is not 0, population slope. Here we're talking about the population correlation, rho. Is it 0 or not? It's the same t-stat, same p-value. You're essentially testing the same thing when you do these tests. I mean, you're thinking about them differently, but they are testing the same thing. That should make some sense because rho is positive, actually, it turns out, when B1 is positive. It's negative when B1 is negative, and it's 0 when B1 is 0. Okay, I'll let you think about that. Yet more calculations to check. I hope you're hanging with me here. Let me say one more thing here before I go on, though, to think intuitively. One thing to emphasize is that these intervals here, the confidence interval and prediction interval, do get smaller the closer x is to x bar. I don't remember offhand what x bar is here, but when x equals x bar, in fact, this is going to be 0 here and here. And these margins of errors in these intervals are going to be as small as possible. So when you're close to the sample mean in the x direction, x bar, you get smaller margins of error for both these confidence intervals and the prediction intervals. When you get further away from x bar, when x gets far away from x bar, these fractions that you see here and here get large, relatively speaking, making the margins of error larger, and you get graphs that go away from the regression line for these confidence intervals if you graph them as functions of x, and I will show you that here in the Mathematica. I guess I'm saving the Mathematica and the spreadsheet for the end here. Try to get through these formulas first here, I think. More calculations to check as homework. Define and compute the sum of squares regression, SSR. This R does not mean residual, it means regression. Careful. SSR is actually, for my students, a quantity we've never talked about before. It is still a sum of squares, as you can see, so it's still an SS. R stands for regression. This is measuring, so to speak, the variation of the y-hats about y bar. So if you imagine a regression line being graphed, say like this, like my hand is doing, and if you imagine graphing y bar horizontally, you're measuring the variability from the regression line from that horizontal line. That's called SSR. And you should check that it equals this huge number here. What number is that? 1,730,848,154. You should also confirm that you get the same answer. If you compute B1 times SSXY, that formula is in this book for my students. Double check that you get the same answer. There's another way to compute SSR. Also confirm that if SST, sum of squares total, is defined to be SSYY, that's 17398499121. You've already computed SSYY there, so there's really nothing much to do. However, something that you should do is confirm these equations. SST equals SSE plus SSR. this total sum of squares, the total variation in the y values, which is given by SSyy. This is measuring their variation about y bar, the y values, the y coordinates of the data points, can be split into two other sums of squares. This is ANOVA, analysis of variance. We're looking at analyzing, decomposing the variability in the y values. So you've computed SSR already. You've actually already computed SSE, so just check that the sum of those two numbers does equal SST, this number right here. And therefore, this equation would then obviously be true because we're just dividing everything by SST. Also confirm that R squared equals SSR divided by SST, and equals this thing, which is what we got before. So this is also true. This is really important, actually. What this is emphasizing is that, imagine back to the original graph, okay? Okay, I'll show it to you again. This graph here. In this graph, it's a very strong linear trend. R is very close to 1. R squared is also very close to 1. You can see the R squared value here, by the way, in this output, 0.995. Almost all the variability in the y coordinates of these points is explained by the regression line. 99.5% of it, in fact, is explained by the regression line. There's very little residual variability. These points hug the line pretty closely, including the outlier. Those residuals on a relative scale are pretty small compared to the total variability on this total big scale. So SSE is relatively small, even though it's a big number. SSE is a big number here. This thing right here, 9,967,000.414, is a pretty big number. But compared to numbers on the order of billions, like SSR and SST, it's relatively small. R squared here is almost equal to 1. SSR is almost equal to SST. SSE is very small compared to SSR and SST. This fraction here is close to 0. Okay? So that's emphasizing that R squared, this percent, about 99.5%, gives the percent of the variation in the y values that is explained by the regression line of y on x. Okay? Those points are practically on that line on that large scale. Again, the residuals themselves and the squared residuals are fairly large numbers in the big scheme of things. When you look at those, you'd say those are large numbers. But compared to SSR and SST, they're relatively small. Very strong regression here. This is the final slide of calculations to check. Then I'm going to show you more in Mathematica and a spreadsheet. And this will come out especially on those things as well. Something called the ANOVA F statistic. And again, ANOVA stands for analysis of variance, and it has more importance for us later on with multiple regression and categorical ANOVA. The ANOVA F statistic we want to compute. And we'll see it again in the output, both in Mathematica and in the spreadsheet. First, compute something called the residual mean square, or error mean square, symbolized this way. MS sub E, take SSE, sum of the squares of the errors, the residuals. There's no R there, even though residual starts with an R. And divide it by its DF, its degrees of freedom, which in general, for multiple regression, DFE is n minus k minus 1, where what is k? K is the number of predictor variables, the number of explanatory variables. X in this case is our predictor variable. There's just one of them. So for this case, with simple linear regression, single variable linear regression, k is 1. And this degrees of freedom of the error simplifies to n minus 2. 12 in this case. So if you take SSE and divide by 12, you should get this number. Confirm that. We next calculate something called the regression mean square, MSR, where we take SSR, sum of squares regression, not residual, and divide by the regression df, which is defined to be k in general, but for our case is 1. So we divide for this simple linear regression, we divide SSR by 1, meaning we get SSR in this case. That's called the regression mean square. There's something called an F statistic where we divide these mean squares by each other. We take the regression mean square and divide by the residual mean square, or the error mean square. And it turns out to be a pretty big F statistic, 2,307.5 approximately. And if you go to the F table, based on 1 in 12 degrees of freedom, you'll see it's off the charts. The p-value is tiny. You can use your calculator to calculate the p-value, and you get the same p-values before. 4.3 times 10 to the negative 15th for that test. Beta 1 is 0 versus beta 1 is not 0, which again is equivalent to the test rho is 0 versus rho is not 0. Notice I'm not multiplying this p-value, this probability symbol by 2, whereas I did with the t statistic. That's because the t statistic is symmetric, about 0, and we need to double the one-tailed p-value. The F statistic here is already set up, so to speak, to compute a two-tailed test p-value, and it is approximately the same thing as before. Maybe I should show you these things on a calculator here as well before I go to the Mathematica and the spreadsheet. Okay, so what was the t statistic value? First, let's confirm that. That was 48.037, let's say approximately, 48.037. So I'm going to go to the distributions menu. I could do tests as well probably, but let's do it in terms of a t CDF here. That's one way to compute this. That'll emphasize that it's coming from a distribution. Again, I could do tests. I'm not sure that the calculator has the F-stat test. I haven't checked before. So again, we're trying to find the area under this to the right of 48.037. So I could put a 48.037 here and say a 10 to the 99th here. 12 degrees of freedom. So this should be half the p-value we got, because this is going to be one-tailed. Yep, if I multiply that by 2, I get 4.33 times 10 to the negative 15. Again, I probably could do it with the test menu as well. The stat test, actually. Yeah, this one here. With the t-test, I could do it that way as well. I don't know if the stat menu has an F. It looks like it doesn't have an F. So let's go back and check the F1 with the distributions menu. The distributions menu does have an F CDF. The value of the F statistic, though, is not the 48. It's the 2,307.55, say. 2,307.55, 10 to the 99. 1 was the degree of freedom in the numerator, and 12 was in the denominator. That gives the same number up to some rounding as before, and we don't need to double it. Okay? All right, let's finish by looking at more about Mathematica and the spreadsheet. I haven't shown you the spreadsheet yet. So we're going to go down here and look at other things that linear model fit can do. So I'll enter these things and try to remind you how it's related to what I said in the PowerPoint. We can find R squared, the coefficient of determination. There it is, 0.995. What was I doing earlier? I did the linear model fit. And I stored the output in a variable I call LM. I didn't have to call it LM, by the way. I could have called it something else. So there's nothing special about the LM. But what is special is what you put inside the square brackets here. The quotation marks and R squared, capital R, capital S, gives you the value of R squared. I can get an ANOVA table. Not quite as extensive as what we'll see in the spreadsheet, a partial one. It looks like this. Actually, that is completely what you see in the spreadsheet. There's something else in the spreadsheet that we don't see here. So what do we have here? We have these different DFs, first of all. The df for the x here is the regression df. Error is synonymous with the residual. This is the df for the error. This is the n minus 2. The total EDF is n minus 1 always. 13 is n minus 1. 1 plus 12. This is the regression SS. SSR, relatively big, that's over 1 billion. This is SSyy, sum of squares of the errors. This is SSR, this sum of squares for regression. I might have said DF. This is SSyy, over 1 million, but that's, you know, pretty small compared to 1.7 billion. This is the SST here. The sum of these two does equal SST. MS R is SSR divided by DFR, and when you divide by 1, it doesn't change it. MSE is SSE divided by DFE, and you should check you get this. And this number, the F statistic value, is MSR divided by MSE. And the p-value here is the same as before, 4.33 times 10 to the negative 15. This is a parameter table. It's giving us the slope and the intercept. This is the intercept here. This is the slope here. These are standard errors. This 0.025, that's what I drew on the paper. I guess I didn't draw as much in the paper as I was thinking I was going to, but that was what I drew on the paper. This is the standard error for the intercept. It's much bigger. Okay, the sampling distribution of capital B0 has a much bigger standard deviation, much more variability in the intercept based on this sample from a wider population. The t statistic, here's the one we got before, and here's the same p-value we got before for the same test. Beta 1 is 0 versus beta 1 is not 0. It's automatically assuming you're doing a two-tailed test here. So if you wanted the one-tailed p-value, you'd have to divide it by 2. The t statistic to test whether the intercept, beta 0, is 0 or not is very close to 0. The p-value is very large. You definitely do not have strong evidence that beta 0 is non-zero, where beta 0 is the population intercept, not slope. P-values can be written in a list, same as these two numbers here and here. We can do confidence intervals and prediction intervals. We can do it with a table. Actually, excuse me. This is not confidence and prediction intervals that I could talk about before. These are confidence intervals for estimating beta 0 and beta 1. This be a confidence interval to estimate beta 0, the population intercept. Notice it contains both positives and negatives. We, again, do not have very strong evidence that beta 0 is non-zero. But the confidence interval to estimate beta 1 only includes positive numbers. We definitely have strong evidence that beta 1, the slope, is non-zero. We can highlight these confidence intervals like that as well, and we can use a different confidence level. The assumption is here that you do a 95% confidence interval, but we can change it to, for example, 99%, and you can see these intervals are bigger because you want more confidence. Yes, we can do prediction intervals and, oh, that's down here, prediction intervals and confidence intervals. Confidence intervals to estimate the mean response, prediction intervals to estimate an individual response. We can also look at the y-hat values and the residual values with this code here. These are the y-hat values, and there are the corresponding residuals. You can double check those. We'll look at the spreadsheet and see those as well. And here, yes, our mean prediction bands. These are this formula for what I was trying to say is graphs of the prediction bands. I can plot these things here actually. Two functions to plot. I can actually put it inside a list with curly braces here. Plot it as a function of x. X goes from, say, 0 to 60,000. And we see two, let's make it go further, two curves. Not quite that far. Okay. We see two curves that represent the extremes of confidence intervals to estimate the mean response for any given x. And notice that this is skinniest vertically when x is close to between 10 and 20,000, and it gets further wider the further away you go. X bar must be something between 10 and 20,000. We'll see what it is here in a minute. Okay, because that's where this is skinnier. That's where I was trying to make these drawings with my hands. We can plug in a number into it, like 7,681. Oops, not into that though. The percent sign refers to the preceding output. To get a confidence interval to estimate the mean response when x is 7,681, so this would be the mean tuition in 2019 for schools whose tuition in 2013 was approximately this. I wrote this on the PowerPoint. We could also do that with one bit of code just like that. And here we can also do prediction bands. Now let me just copy and do the plot again. Well, before I do the plot, I should probably do this. I should evaluate this as 7681 because of the percent sign there. Now let's do the plot, and let's copy and paste these formulas. These are going to be a bit wider because these are prediction intervals. Wider in the vertical direction. So you can see those are a bit wider because we're talking not about estimating the mean response, but individual responses. You want to think about any given x. The y coordinates on these points are the lower and upper bounds of your confidence or prediction interval. You can plug it in right away. This should be one of the answers on the PowerPoint. And these two things give you confidence and prediction intervals based on the data. That's maybe not actually so useful because you already know what the data is. Based on the given x values, the given 2013 tuitions for the data. All right, let's go to the spreadsheet and then we'll be done. I know this is not the most exciting thing in the world to be trying to watch, but it is important if you really want to learn this stuff well. So in the spreadsheet, I got here, here's the data. The university's over here. The x and y values are in these columns. I went wild on this, filling in a lot of different stuff, using some formulas even that I haven't talked about before. There's, for example, there's a and using built-in functions like to find the correlation, I used equals correl like that. And there's a formula for the slope that I actually haven't talked about that I used right here. So if you do look at the spreadsheet, the formula that I used for the slope is different right there. It's not the one that I shared with you. Anyway, on the spreadsheet we also have columns for x squared, y squared, x times y. Those are the formulas in the summations we're going to need in the normal equations. Those summation values are down here. I should also note that x bar is between 10,000 and 20,000 like I was just talking about a few minutes ago. It's about 13,000. So the prediction and confidence intervals when you know x are smallest when x is very close to 13,000. That's where they're skinniest. I got the y hat values over here, calling them y hat. I got the residuals or errors in this column and the squared residuals in this column. These numbers, the y hats are the predicted values and the residuals are in the Mathematica output that I just showed you like 2 minutes ago. Those last 2 lines of code are these numbers here. SSyy sums up the squared residuals down here. That's SSyy. I also have some summary output that I had to obtain by going to add-ons and making sure I had the Excel minor analysis tool pack here. This summary output of the spreadsheet here contains the ANOVA output. This is the same thing that I showed you in Mathematica before, just 5 minutes ago or so. It contains this stuff here. This is the same thing I showed you in Mathematica as well, although in Mathematica it was split into 2 different tables. But the same B0 and B1, same standard errors, same t-stats, same p-values, same confidence intervals to estimate beta 0 and beta 1. I also did have the spreadsheet make a residual plot, and you got the outlier there. Very good random scatter in here. This outlier is, well, it's an outlier, but it still has a positive residual. I did compute y hat squared values. It turns out because that helps you compute SSR. and you can confirm that that's the same as this number here. And yes, SSR plus SSE does equal SST, which I've also called SSYY. So many symbols, so many equations. And yeah, this seems like, in summary, a pretty good model. And yes, finally what I did was I used the model to make confidence intervals and prediction intervals. Confidence intervals to estimate mu, prediction intervals to estimate y, using the formulas, those real complicated formulas involving square root of, for example, 1 plus 1 over n plus x, the 7,600, whatever it was, 81 minus x bar squared divided by SSXX. You kept with me. Hopefully you remember what those are. Mo stands for margin of error. I got standard errors for mu hat and y hat. Those are the square roots times s as well. Regression standard error. This y hat, there's the 9226. The actual y value for Minnesota State universities in 2019 is smaller than the predicted value. So Minnesota State universities, here's a practical conclusion from all this, are doing better with respect to tuition than what you would predict from the model based on Big Ten universities. That would be a significant conclusion you can reach from this. And yeah, these intervals are useful as well to make predictions about what would happen for a randomly chosen school, or the mean of all such schools whose 2013 tuition was close to $7,700. All right, well, that was quite a long thing. I think most of my lectures are going to be shorter than that, but we won't need to review a lot of things. Thanks for watching.